All right, hello class. In this video, we're going to be talking about our basic derivative rules. So the motivation here is that using the limit every single time to find the derivative is pretty tedious, and we want to be able to do this quicker, essentially. Okay, so we are going to see if we can establish patterns or rules that will let us differentiate more complicated things. Because, for example, if I wanted to find the derivative of something like x to the 3/2 using the limit definition, or maybe more something like 5/7, x to the 5/7 would be rather difficult to do. Or something even crazier like x to the 7/5 plus 3x squared plus 1 over 7x to the 10th plus 10. If we wanted to use the limit definition here, this would just be a nasty limit to have to calculate. Okay, because we'd have to put x plus h into here, and then x, and then subtract, and then simplify. And honestly, there's a lot quicker way we can do this, and that's what we're going to be focusing on now. Okay, before we really get rolling, I want to look at some more general properties of the derivative and how they work. And it turns out that our constant multiplication and sums work out exactly how you would expect, hopefully. So to start with, if f of x and g of x are differentiable functions, okay, and c is a constant, then we have the following properties. That if we, the first one, which is going to be our constant multiplication, if we want to take the derivative of a constant times a function, right? Well, that's going to be, say, the limit as h goes to 0 of that constant times f of x plus h minus the constant times f of x all over h. And what's true of limits is going to be true here. We can basically take this or factor this constant out, and since the limit is not affecting the constant, it's just affecting the h essentially, we can move this out to get c times the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is just the derivative of f of x. So that's going to be c times the derivative of f of x, or c times f prime of x. So simply, constants come along for the ride if they're multiplying. Okay, so for example, last time we looked at say this function here, x to the 5th. We, with the limit definition, found that if f of x is x to the 5th, then f prime of x is 5x to the 4th. Okay, what this means for us with the constant multiplication is that if we have this other function, let's say g of x is 10 times x to the 5th. Okay, well, if that's the case, then g prime of x, well, the constant just comes along for the ride, and then we just multiply by whatever the derivative of this x to the 5th is, which is 5x to the 4th. Right, so it's 10 times 5x to the 4th, which that is the derivative of the x to the 5th piece. It's just going to come out to be 50x to the 4th. Okay? So that's what I mean by saying that constants just come along for the ride. Okay, so another example. In our last video, we showed that the derivative of the square root of x is 1 over 2 times the square root of x. So similarly, if we want to take the derivative of, let's say, 8 square root of x, it would simply be 8 times the derivative of the square root of x. Okay, we can move the constant outside, and it will just be 8 times 1 over 2 times the square root of x. And the 2 will cancel with the 8, and we'll end up with 4 over the square root of x. Okay, so notice here, I didn't have to go through the limit to do this. We've already found the derivative of x to the 5th and square root of x. That means we also have the derivative of any constant times x to the 5th, right? When we differentiate it, it's just going to be that constant times 5x to the 4th. And we have the derivative of any constant times the square root of x. When we differentiate that, it's just going to be that constant times 1 over 2 root x. Okay, so this is the first thing that will simplify our lives, because once we have one derivative, we have the derivative of the constant, any constant times it as well, because the constants just come along for the ride. All right, next up is sums. So if we want to take the derivative with respect to x of f of x plus g of x, okay, and we use our limit definition. So the limit definition of the derivative is plugging x plus h into the function. So in this case, it will be the sum f of x plus h plus g of x plus h minus just the function left alone, so f of x plus g of x, okay, all over h. If we distribute, okay, that negative and also sort of group our like terms, so we group our f's and our g's together, we're going to get this, f of x plus h minus f of x, then plus g of x plus h minus g of x. And this is going to be all over h, which we can actually split up this fraction since and have it like this, that it's the f of x plus h minus f of x all over h, and g of x plus h minus g of x all over h. And the nice thing about the limit is that we can distribute it across addition. Okay, so I'll have the limit as h goes to 0 of f of x plus h minus f of x, okay, all over h, plus the limit as h goes to 0 of g of x plus h minus g of x all over h. Okay, so, well, this is the definition of f prime, and this is the definition of g prime. So it turns out that you can just take derivatives term by term, just like you can with limits, right? So, for example, if we have this function f of x is 4x to the 5th minus square root of x, f prime, well, we just take these derivatives piece by piece, right? So the constant comes along for the ride, and so it'll be 4 times 5x to the 4th. Now, minuses, we still use a sum rule, because this is technically 4x to the 5th plus a negative 1 times the square root of x, right? So that negative 1 comes along for the ride to give us plus, let me put this in parentheses, okay? So it'd be plus, then times negative 1 times the derivative of the square root of x, which is 1 over 2 root x. Okay, and so if we were to simplify this now, we would get 20x to the 4th minus 1 over 2 root x. All right. So that's how sums work. Okay, so we have these nice rules for constant multiplication and sums. What about products? Okay, some of you may find it odd that I'm jumping straight to the product rule here, if you've seen this before, but there's a method to my madness here. But what about products? Does, say, the derivative with respect to x of f of x times g of x equal f prime of x times g prime of x? Well, that would be nice. Unfortunately, it's not, because we can see it right here. We have the derivative of a constant times f is that same constant times f prime. Now, if this were true, right, if the derivative of, the derivative of a product was the product of the derivatives, this could not be true. So the answer is going to be no, because if we want the derivative of a constant, right, well, a constant function, no matter what we plug in, right, if f of x is equal to c, then f of x plus h is also equal to c. Right, so if we take the limit as h goes to 0 of f of x, well, let me not call it f here, but basically c minus c over h, that's just 0. Right, the derivative of a constant is 0. So if this property were true, then the derivative of everything would be 0, right? Because the derivative of f of x we could always write as the derivative of 1 times f of x, which, if this property here were true, this would be the derivative with respect to x of 1 times the derivative with respect to x of f of x. And the derivative of 1 is 0. Right? We'd get 0 times f prime, which would be 0. So if this property is true, the derivative of everything is 0. And we know that's not true. So no, this is not true. It'd be nice, but it's not. Okay? This is one of the biggest mistakes I see with people who don't, say, remember the product rule that we're about to talk about. Okay? But yeah, no, unfortunately this is not true. And here's why. Right? When we try to set up the limit definition of a product, unlike with the sum, we don't have a nice way to break these apart, right? Because I'll have f of x plus h times g of x plus h minus f of x times g of x all over h. So unlike with the sum, where we could group the f's and the g's together and just split it apart, we don't have that now because they're intertwined. Okay, so what we're going to do is, and this is a really funky trick, okay, maybe a bit advanced, but we are going to add and subtract by the same thing. So this is kind of like our conjugating factor, where we would multiply the top and the bottom by the same thing, multiply by a funky version of 1. Now we're going to add by a funky version of 0. We're going to add and subtract by the same thing, and the reason we're going to do that is because it's going to allow us to factor and split things apart. Okay, so I have the f of x plus h times the g of x plus h. And what I'm going to do is I'm going to subtract here by, let's do f of x times g of x plus h, and then I'm going to add by the same thing. This is very similar to a conjugating factor, okay? Right, because what we are doing is basically adding and subtracting the same thing. So this is basically adding 0. May seem strange, but you can always add by 0. You can always multiply by 1. All right, and then we already have the f of x times g of x here. Now, you might wonder, why would we do this? Well, it's simply because if we were to break this up into two groups now, say this group and this group, okay, we can actually factor things out now. In this group, they both share a g of x plus h, and in this group, they both share an f of x. Okay, so we can actually factor. This will be the limit as h goes to 0 of, let me go ahead and factor it out, g of x plus h, okay, times f of x plus h minus f of x all over h. Okay. And then plus, and in this case, we can actually factor out an f of x. Okay, so we have the f of x times g of x plus h minus g of x. Right? And everything here is all over h. Now, I'm going to rewrite this a bit. I'm going to split up this fraction. I'm going to distribute this limit across. Okay, so I'm going to have the limit as h goes to 0 of, I'm going to write this a little differently. I'm going to write it like this, f of x plus h minus f of x all over h, and times g of x plus h. Right, so there's our first piece. And the second piece will be the limit as h goes to 0 of f of x times g of x plus h minus g of x all over h. All right, now, this piece, as h goes to 0, okay, that's going to f prime, and this piece, as h goes to 0, is going to g prime. In fact, we can split up the limit even further to do this. All right, I spared you the torture of watching me write all this out, but basically you can distribute limits across products this way, and then now each individual piece, well, this is basically f prime. This, well, there's nothing here messing with the limit, right? There's no division by 0 here, so we can just let that h go to 0. Okay, so this is just going to g of x. This, well, there's no h here at all, so really we could almost consider that a constant, and then this is going to g prime. Okay, so the whole thing ends up being f prime of x times g of x plus f of x times g prime of x. All right, so at the end of the day, when we take the derivative of a product, f of x times g of x, okay, and I like to write this without the of x's just to make it look a little more simplified. Okay, so the derivative of f times g is going to be f prime times g plus f times g prime. Think about what we're doing. We are taking the derivative of f and leaving g alone, then adding, leaving f alone, and taking the derivative of g. Now, will this jive with what we already know about constants, right? Turns out it will, because if we take the derivative with respect to x of a constant times f, and let me put of x here, just so it's clear here, it's going to be the derivative of the first, which is the derivative of a constant, okay, times f left alone, plus c left alone, times the derivative with respect to x of f. Okay, well, the derivative of a constant is 0, so you get 0 times f of x plus c times f prime. Well, that goes away, and you just end up with c times f prime of x, and there we go. That actually satisfies what we already know about constant multiplication. Okay, so to apply this to what the rules we've already established, the derivative of x to the fifth times square root of x is now going to be, well, it's the derivative of the first, 5x to the fourth, okay, times this second guy left alone, okay, plus the first guy left alone, x to the fifth, times now the derivative of the second guy, which is 1 over 2 square root of x. Now what's interesting about this is we have actually given ourselves a new way to know about derivative rules, because derivative, well, x to the fifth times the square root of x, well, the square root of x is just x to the 1/2. Okay, and when we multiply powers like this, we add the exponent. So this will be x to the fifth plus 1/2. Okay, and 5 is also known as 10/2. So what we're actually looking at here is the derivative of x to the 11/2. Now, if we simplify this side, the right side of this equation, we'll have 5x to the fourth times x to the 1/2 plus x to the fifth times 1 over 2 times x to the 1/2. Now, whenever you have an x in the denominator, you can bring it up as a negative exponent. Right? So we'll get 5x to the 4 plus 1/2 here. Okay. Then plus, I'm going to move the 1/2 outside. X to the fifth minus 1/2. Oh, sorry. Let me actually write this out explicitly here. It'll be x to the negative 1/2. So remember, whenever you have an extra power in the denominator, you can bring it up as a negative exponent. Okay, so this will be 5x to the, that'll be 8/2 plus 1/2. Okay, then plus 1/2 times x to the, if we want to put this in halves, that's 10/2 minus 1/2. All right, so we end up with 5x to the 9/2 plus 1/2 x to the 9/2. Oh, well, now these are like terms. And so if I change this 5 to a 10/2, we're going to get, when we bring these together, 11/2 x to the 9/2. Okay, so what we've essentially done here is given ourselves a rule for the derivative of x to the 11/2, which ends up being 11/2 x to the 9/2. Well, hang on. The derivative with respect to x of x to the fifth was 5x to the fourth. And then the derivative with respect to x of square root of x, which is x to the 1/2, was 1 over 2 root x, which we could also write as 1/2 x to the negative 1/2. Are we seeing a pattern here? I'm starting to see a pattern where the derivative of x to the fifth, well, there's a 5 out front. And then the exponent is 1 less, right? Because this is 5 minus 1. And we have the same here. When we take the derivative of x to the 1/2, well, the 1/2 is out front, and then 1/2 minus 1 is actually negative 1/2. Oh, and 11/2, we bring that out front. It's 11/2 times x, and what's 11/2 minus 1? Well, it's 11/2 minus 2 over 2, which will be 9/2. Oh, is this always true? Well, let's see. Okay, to begin our examination, let's find the derivative with respect to x of just x. So that's going to be the limit as h goes to 0 of x plus h minus x all over h. Okay, so we'll get the limit as h goes to 0 of, well, the x's cancel, so we get h over h, and so that's the limit as h goes to 0 of 1, so that will just be 1. Okay, so the derivative with respect to x of x is 1. This also means, based on what we've already seen, is that, say, the derivative with respect to x of 2x is going to be 2 times 1, which is 2. And more importantly, right, the derivative, let me do it here, the derivative with respect to x of mx plus b, hopefully this is familiar as the equation of a line, is going to be m times 1 plus 0, since the derivative of a constant is 0, and then a constant multiplying a function comes out to be, or it just comes along for the ride. Okay, so we end up getting m. So the derivative of a line is always equal to the line's slope. Hopefully that makes sense, because a line has what's called a constant rate of change. Okay, and a constant rate of change means it's always changing by that same amount, right? That same rate. And it turns out the derivative aligns with that. All right. Next up, let's find the derivative of x squared. Now, I'm going to use the product rule because I can rewrite x squared as x times x, right? So I'll have the derivative of the first times the second left alone plus the first left alone times the derivative of the second, since we already know the derivative of x. So we get really x plus x, which is 2x. Oh, that looks the same. We bring the 2 down, and then the exponent here, which is 1, is 2 minus 1. Okay. How about the derivative of x cubed? Well, we can rewrite x cubed as x squared times x and use the product rule, right? Because the product rule, well, it'll be the derivative of the first, which we've just done. The derivative of x squared is 2x, right? Times the second function left alone plus the first function left alone times the derivative of the second function. Right? So you can think of this as f prime times g, then f times g prime, if this is f and this is g. Okay? When we simplify this, we're going to get here 2x squared plus x squared. So this comes out to be 3x squared. Well, what do you know? You bring the 3 down, and then the exponent is 3 minus 1. Okay? How about x to the 4th? Well, again, the derivative of x to the 4th, I could rewrite this as x squared times x squared and then just use the product rule again, right? We'll have 2x, derivative of the first times the second left alone, plus the first function left alone times the derivative of the second function. And here we have 2x, x squared, so that is going to be 2x cubed plus 2x cubed, which is 4x cubed. And what do you know? Again, we have moved the exponent down, the 4, and then subtracted by 1 in the exponent. Right? This is, 4 minus 1 up here. Right? We've already done x to the 5th. We did that with the limit definition, so I won't do that again, but I will write that derivative of x to the 5th is 5x to the 4th. Okay, and from this pattern, I can make the claim that the derivative of x to the 6th will be 6x to the 5th. And it is. If we use the product rule, we can show that this is true. And we can do this for basically any power that we want. Now, we've only done positive powers here. Okay. Let's look at some fractional powers and see if it still holds up. Now, before I do that, though, I do want to show that we can extend the product rule to look at multiplications more than just 2 things multiplied together. If there are 3 things multiplied together, what you can do is take the derivative of, say, the first 2 as a single thing together, then times the third. All right, so it would be the derivative with respect to x of the first function times the second function left alone. So just to make that totally explicit here, it's the derivative of the first function times the second function left alone. Then it will be plus the first function left alone times the derivative of the second function. Okay. Now, here we do the product rule. So this, in the big parentheses here, well, the product rule is going to be f prime times g plus f times g prime. And this whole thing is times h. Then I'll plus, well, this is just f times g times h prime. All right? Now, if I distribute this h across, we'll actually end up with f prime times g times h plus f times g prime times h plus f times g times h prime. Look at what we've done. Right? This is the same exact pattern, just continued a step further. Right? The derivative of f times g times h is f prime, so the derivative of the first and the second 2 left alone. Then the derivative of the first, then the first left alone, the derivative of the second and the third left alone, and then finally the first 2 left alone and the third function, we take its derivative. Okay, so this is the pattern that we follow for any product. So for f times g times h times I, we'll have f prime times g times h times I left alone, then f times g prime times h times I, plus f times g times h prime times I, and then finally f times g times h times I prime. So notice, no matter, or however many pieces we start with that are multiplied together, we have that many summons. That's what these things are called. The things that you sum together are called summons. And then we take the derivative of only one of them each time. Okay? If you just remember that, that's going to save you a lot of time because you don't have to do this thing over and over and over again. Okay? You can just go through it straight through like this. All right, now that we have that out of the way, we can start looking at more complicated fractions when we're doing this. Okay, so or more complicated powers of x is what I mean. So, for example, all right, say we want the derivative with respect to x, the square root of x. Right? We already have it. We already know that this should be 1 over 2 square root of x. All right? But say I don't, and I want to use the product rule. Okay? So remember, the product rule, well, I don't think I labeled it exactly like that, but that's what we've been doing with products. Here's how we would go about doing it. And we can take this idea further, which is what we'll end up doing. Okay? So what we can do is say that x is equal to the square root of x times the square root of x for x greater than or equal to 0. Okay, right? When you take the square root of x times the square root of x, you get x, provided x is positive. All right. Then we're going to differentiate both sides. Right? So I'm going to take the derivative of x on this side, and then the derivative, okay, of x, or of square root of x times the square root of x on this side. Okay, so now the derivative of x we know is 1. And if we didn't know the derivative of the square root of x, we could just apply the product rule, because this will be the derivative of the first function times the second function left alone plus the first function left alone times the second function left alone. Okay, so these two guys are pretty much the same thing, just written in a different order. So really, if we combine these like terms, we're going to get 2 square root of x times the derivative with respect to x of the square root of x. Now, if I just divide by 2 root x on both sides, all right, we're going to get 1 over 2 square root of x is equal to the derivative with respect to x of the square root of x. And check that out. We already knew that. We did that with the limit before, but now we have verified it with the product rule. Now, the reason I showed you this is 1, so that you can trust this method, but 2, we can expand this to find lots of things, right? So we can use this to find, say, the cubed root of x, right? It's the cubed root of x. Well, if I take the cubed root of x and cube it, you get back to x, right? So that means that x is equal to, well, 3 cubed roots multiplied together. And here we don't have to worry about x being positive because thankfully the cubed root is defined, okay, for all x. Okay, and now we can just differentiate both sides. Okay, the derivative of x is 1, and the derivative of this, well, we'll apply the product rule. It'll be the derivative of the first function, okay, times the next 2 left alone, okay, plus now the first function left alone, the derivative of the second function, okay, and then the third function left alone, and finally the first 2 functions left alone times the derivative of the third. Now again, I don't know what this derivative is, but we can solve for it now, right? Because now these are all the same, just written in a different order. So what we have is 1 is equal to 3 times the cubed root of x times the cubed root of x times the derivative with respect to x of the cubed root of x. Okay, well, I'm going to rewrite this now as 3x to the 1/3 times x to the 1/3, which is x to the 2/3. Right? Or x cubed squared is x to the 2/3, and this is the derivative with respect to x of the cubed root of x. Okay? Once again, now I'll just solve for this by dividing by the 3x to the 2/3. Okay? So, finally, putting all this together, the derivative with respect to x of the cubed root of x, which is also known as x to the 1/3, is 1 over 3 times x to the 2/3, which is 1/3 x to the negative 2/3. Right? Once again, we bring the 1/3 down, and when we subtract 1 from 1/3, well, that would be 3/3. That's going to be negative 2/3. Okay, that is always going to be the pattern here. Okay, and then from here, we can do all sorts of stuff, like the derivative with respect to x of x to the 2/3 is, well, that's going to be x to the 3rd times x to the 3rd. And then we can just use the product rule. Right? Be the derivative of the first, which is 1/3 x to the negative 2/3 times the first guy left alone. Okay? Then plus the first guy left alone, then times the derivative of the second guy, which will be 1/3 x to the negative 2/3. Again, we have like terms, and x to the negative 2/3 times x to the 1/3, well, that's going to be x to the negative 1/3. Okay, so when we bring these together, we're going to get 2/3 x to the negative 1/3. And once again, we bring the 2/3 down, then 2/3 minus 1, which will be 3/3, is going to be negative 1/3. And that's what our exponent ends up being. Okay, in fact, we can do this with pretty much any exponent, okay? And this is what's known as the power rule. Okay, the power rule essentially says that the derivative of x to any power is just going to be that power times x to the power minus 1. Right? Always. When we do this, we bring the power down and subtract by 1. Right? So it'll be p times x to the p minus 1. Okay, now we've done this with nice positive whole number powers. We've done this with fractional powers. Does this still work with negative powers? All right, of course here the answer, thankfully, is yes, but to show why, we need the quotient rule. Okay, so the quotient rule is sort of a special case of the product rule. Okay, so what the quotient rule is basically trying to find a derivative rule for f over g. Okay, so when we go to find the derivative rule for f divided by g, what we end up doing is we'll call capital Q of x the quotient of f of x over g of x. Okay, and we're basically saying that we don't want g to be equal to 0, right, since we're dividing by it. All right, now instead of just dropping straight to the what the quotient rule is, to find q prime, what we're going to do is just move the g up to get q of x times g of x is equal to f of x. All right, and then we'll differentiate both sides, basically what we've been doing basically this entire time. Right? It's actually kind of interesting that we can find pretty much every rule from some very basic properties and the product rule. Okay, so here we're going to use the product rule. Right, it'll be the derivative of the first, so q prime times g of x left alone plus q of x left alone times g prime of x. Okay, and that's going to be equal to f prime of x. Okay, and now we're just going to solve for q prime, because that's what we're looking for really, is we want to find q prime. So we're going to solve for this. So that means we're going to move this over. So we'll have the q prime of x times g of x is equal to f prime of x minus q of x times g prime of x. Okay, then we are going to divide by g of x. Okay, so we'll have q prime of x is equal to f prime of x divided by g of x minus q of x times g prime of x divided by g of x. Now, this is not a formula we would want to memorize. This isn't very useful. However, we can put the q of x back in. So remember, q of x was f over g. So we can actually put that in. And when we do that, what we get is this is equal to f prime of x over g of x minus q was f of x over g of x. Then we have g prime of x over g of x. Oh, so this is now g of x squared. So we can get a common denominator by throwing in a g over g here. Okay, so that's what we're going to do to get f, let me not change the color there, to get f prime of x times g of x minus f of x times g prime of x all over g of x squared. Okay, and that is the quotient rule. Okay, so here's the product rule again. Remember, the derivative of f times g, or the first function times the second function, is the derivative of the first times the second left alone, plus the first left alone times the derivative of the second. And so with the quotient rule, the reason I write my product rule like this is because once you know the product rule like this, notice that the quotient rule is exactly the same except there's a minus sign and we divide the whole thing by g squared. Okay, or the bottom squared. All right, so you could also think of this as the derivative of the top times the bottom left alone minus the top left alone times the derivative of the bottom all over the bottom squared. Okay, and then you could think of the product rule as the first, right, derivative of the first times the second plus the first left alone times the derivative of the second. So I'll just put sec for second. Okay. So one thing to notice though is with the product rule, it doesn't really matter what order you do this in. Okay. However, with the quotient rule, it does, because if you mix these up, you're going to get the negative of your right answer. Okay. All right, now how this helps us is whenever we have a negative power now, well, negative exponents are essentially just fractions. Right, so for example, if I wanted to take the derivative of x to the negative 7/5, well, I could instead think of this as the derivative of 1 over x to the 7/5, because with negative exponents, you just can move them down into the denominator. And so now we can apply the quotient rule, right? From the quotient rule, we'll have the derivative of the top. Well, the derivative of the top is just 0 times the bottom left alone minus the top left alone times the derivative of the bottom, which now we can apply the power rule, which will be 7/5 times x to the 7/5 minus 1 all over the denominator squared. Okay, so what we'll end up with is, well, this whole thing here just zeroes out. Okay, and we'll end up with negative 7/5 x to the 7/5 minus 1. So that's 7/5 minus 5/5 all over x to the, well, 7/5 squared is going to be 14/5. Okay, and so this is going to end up being negative 7/5 times x to the 2/5 all over x to the 14/5. All right, well now we can bring that up as a negative exponent and have 7/5, or negative 7/5, times x to the 2/5 minus 14/5. Okay, so that will be negative 7/5 times x to the negative, that's going to be negative 12/5. Okay, well, turns out that if we just use the power rule, right, x to the negative 7/5, if we move this negative 7/5 down, well, that's what we have here, right, negative 7/5, then x to the negative 7/5 minus 1, well, that's going to be minus 5/5. Oh, and negative 7 minus 5 is negative 12, so we're going to get negative 7/5 x to the negative 12/5. So all of that was to show that the power rule works perfectly fine with negative exponents via the quotient rule. All right, so our power rule, x to the p, being p times x to the p minus 1, this is going to be true for any p, which is super nice, because now if I say I'm out in the wild and I need to find the derivative of something like the 10th root of x, well, that's just going to be x to the 1/10, and we can move the 1/10 down and make this x to the 1/10 minus 10 over 10. So it'll be 1/10 x to the negative 9/10, and there we go, that's it. Okay, that's all there is to finding derivatives that are of the form x to some power. All right, so I'm going to put a cut in this video and come back and talk about some of the more complicated functions, because now we've done x to a power, okay? But now we need to talk about stuff like e to the x and our trig functions and things like that. And then I just want to look at a bunch of examples, okay? So we'll come back in the next video and sort of look at the other rules and then examples. All right, and I'll catch you.